Awesome. Thank you guys for coming. It's a pretty small crowd, so that means if you would like to unmute yourself, feel free to. If there's anything you want to add or comment, by all means, go for it. It's going to be a relatively short meeting. We're just going to be going over what support vector machines are on a high level, and we're going to go ahead and also build our own classifier to see if a tumor is malignant, meaning cancerous, or benign, meaning not cancerous. So if there's something you don't understand or you want me to explain more, I can go ahead and do my best and go over that part. But yeah, let's go ahead and get started. Cool. So we're going to be going over what is SVM, applications of SVM, and implementation. If I were to give you a rough time estimate of how long this meeting would take, I would say probably about 30 minutes. I don't want to keep you guys too long, and hopefully you can get as much information from this workshop as possible. So cool. So what are support vector machines? Well, support vector machines are basically a supervised machine learning algorithm. So if you were here for the last workshop, we went over what supervised machine learning is. This is just another algorithm you can use to implement for certain models. Now, usually we use support vector machines or a support vector machine learning algorithm when we're dealing with many dimensions. So typically from the last workshop, what we did was we worked on KNN, and KNN really works best when we have a lot of data points. But when we're dealing with a lot of dimensions, a lot of features, support vector machines typically work a little bit better. So what is our end goal in using a support vector machine algorithm? Well, our goal is to find a hyperplane in an n-dimensional space that basically classifies the data points. Now, what do I mean by that? Well, I'm just going to go to the next slide real quick. So here we go. Right here, this line right here on this two-dimensional graph is what our hyperplane is. And what that hyperplane is used is to separate clusters of data points to help us classify what those data points are. And basically, you see these two lines here drawn. That is the maximum distance that we want to obtain when separating our points. And that's because we want to make sure that we can separate these points easily and see what the two clusters are clearly. Now, the thing is, if our distance between those points are closer together, so like in this example right here, well, this is an example of what a bad hyperplane is. Because if I were to insert a point right over here, right, you would see that it's closer to the cluster of green points. However, just because our hyperplane is like poorly developed, it would classify this point as a red point. Does that make sense? So ideally, our goal is to identify what the best hyperplane is that obtains the maximum distance between the cluster of points. That will help us classify what point should a cluster what cluster should a point fall into. So if I were to go back, there's many possible hyperplanes that can be chosen to separate the two classes of data points. So like I mentioned, this is one hyperplane, this is another hyperplane. If I were to, I could annotate, let me just give me 1 second. Right over here, this could be another hyperplane, this could be another hyperplane, this could be another hyperplane. You can have whatever possible combination of hyperplanes you want, but the objective is to make sure that we identify the best hyperplane. And the way you identify the best hyperplane is like what I mentioned before, where you maximize the distance between the clusters on each side. Let's go back 1 second. Okay, yeah. And I mentioned that point right there. Cool. So let's keep moving forward. So here's another diagram that kind of accurately shows how many different hyperplanes you can really come up with, and you can find what the optimal hyperplane is. So like here, you can see that the maximum margin, or also known as distance, is where the cluster of squares is the most furthest apart from the cluster of circles. Therefore, this is what our optimal hyperplane would be compared to all the other hyperplanes. So typically when you're working with SVMs, you're working with many features and many different attributes. So when you're working with many different attributes, you typically are working with more dimensions as well. And when you're looking at more dimensions, you could see that, okay, this is what our graph looks like on a two-dimensional graph. But if we're looking in the third dimension, you could see that our hyperplane is this rectangle right here, and it helps us separate our cluster of red points and our cluster of green points. And like I mentioned before, this is when we're using multiple attributes to, classify what our data points are. And just a little bit of a heads up, if you're interested in learning more about the mathematical formula of hyperplanes using kernels and the kernel function, I'm not really going to go into that much because this is supposed to be more of an introduction. You typically learn more of that in like a graduate level course like data mining. But you, by all means, there are really good resources out there like Medium, where you can read into what the math is behind an algorithm. So it's really useful. Okay, cool. So what are some applications of support vector machines? Well, there's a whole variety of things you can use this algorithm for. Time series analysis, classification, which is what we'll be using it for, anomaly detection, regression, machine vision, and text categorization. So here's some more examples. We're going to be using or implementing an SVM algorithm for a cancer diagnosis and prognosis classifier. But you can use it for other things too, like speech recognition. Text classification is a really big one as well. There's really a whole variety of different projects you can work with when using SVMs. Cool. So like I mentioned before, there are certain advantages to using SVMs over KNN. So typically when we use KNN, it outperforms the SVM when your training data is a lot larger than the number of features we're using to classify our data. However, if we have more features that we are using to classify what our data points are, SVM is the better machine learning algorithm to use in this case. So that's pretty much the main distinguishing factor on when you should use SVMs and when you should use KNNs. Cool. So now here's the basic logistics of how the program that we will be implementing works. So on a more advanced level, this is not how the model will be implementing works, but this is typically when you're working in the industry, and if you want to see what it works like, this is how it goes. You have a cancer database, and you have a data preprocessing scale that goes into a split database. And then you split your data into your training data and your testing data, and that training data will be used to train our classifier. And eventually, once we achieve a high enough accuracy for our model, we can use that on the test set and evaluate how good is our classifier, right? So essentially, what is our objective for our classifier? We want to classify whether a tumor is benign, which is not cancerous, or malignant, which is cancerous. I'll be talking a little bit more about what makes a tumor benign and what makes it more malignant in the next slide. From there, we're going to be extracting several features. So that could be fractal dimension, the symmetry of the tumor, the concavity, the compactness, smoothness of the tumor, all those different features. We're going to, after we extract those features, we're going to develop our model and train our model using the training data, and finally apply it to the testing data to determine whether the tumor is benign or malignant. Okay, so quick biology lesson. I'm not a biology major, so I don't know too much about this, but I did some background research, and this is definitely what I understood. So benign tumors typically grow slowly and have distinct borders. They don't invade surrounding tissue. Essentially, benign tumors are the non-cancerous tumors. They don't have the more, I would say, more lethal effects compared to malignant tumors. So malignant tumors typically grow quickly, and they have like irregular borders, meaning they're not really smooth, and they actually invade other tissues. You can see here, the cells are cancerous and they can spread to other tissues and organs, whereas in a benign tumor, the cells are not cancerous and they won't necessarily spread. So, fun fact is when the cells can spread to other parts of the body, that's known as a process called metastasis. And yeah, it's a really cool, fun fact. It's a serious fact, but it's fun to know about. Moving forward. So the features that we'll be using to analyze whether a tumor is malignant or benign include like mean radius, mean texture, mean perimeter. There's a whole bunch of, I can't remember the count, I think around I'm going to say 30 different values that we're going to be looking at. So concavity error, smoothness, mean compactness. And these attributes are all going to be used from a data set within the sklearn library. sklearn has a lot of useful libraries you can use. It has pre-processed data that you can use to build your own model. So meaning that you don't have to really clean your data or figure out how to figure out what attributes you want to use. It provides all the attributes with clean data for you. The whole purpose of using this data set is so that you can easily focus on creating your own model. But yeah, these are the features that we'll be using a trainer model. And the labels, or what we're going to be predicting, is whether our tumor is malignant or benign. Cool. And for those of you who kind of want to follow along, you can find more information about the data set right over here. I will be sending it in the chat, and it's a breast cancer data set for those of you who are interested. One sec. Everyone. Yep. But it just has more information about the data set if you're interested, the number of samples per class, number of classes, and the features. You can look at all of that, and it has plenty of information that I already have discussed. So yep, that's pretty much it. And then if you're interested, you could also find the code on my GitHub, which I will send here. It's open source. There you go. Cool. Anyways, let's keep going. Let me zoom in. Can you guys see this okay? Is that zoomed in enough?
Yes.
Okay, cool. So there's a couple libraries we're going to need. We're going to need sklearn. So since we're working with the machine learning repository within sklearn, we're going to need to import that. We're going to need to import data sets from sklearn to get that breast cancer data set. We're also going to need to import SVM because we're going to be creating our SVM model. And finally, we're going to be importing metrics. Metrics is a really nice library from sklearn that we can use to help evaluate our model without actually inserting the formula of how to compute the accuracy. So that's really useful as well. Cool. So step one, the first thing you want to do is you want to make sure you load your data set. So the nice thing is, like I said before, we're using data sets within sklearn. So you don't have to download any data set or anything. Since it's already within this library, all you have to do is just create your data, call your datasets object, and create your datasets object, and call this function load breast cancer. And what it'll do is it'll load all of that data from the load breast cancer data set and store it into your data table or your data frame. The next thing you want to do is you want to identify all your features and your labels. So this is what you guys saw in that slide I just showed you. But if you want to print out to see what all the features are within the data set, just call the print method, and then you just print out your features within your data frame. And then you can also print out your labels. So that's what I did here. So you can see like some of the features, again, that we're going to be using are mean radius, mean texture, mean perimeter, mean area, and so forth. And by the way, if I'm going too fast, don't worry about it. This meeting's being recorded and it's going to be posted on our YouTube channel. So you can follow along that way if I'm going too fast. Anyways, these are the features that we'll be using a trainer model. And then we have our labels right here, which is malignant and benign. These values are what we're trying to predict for our model to see if the tumor is malignant or benign. The next thing we want to do is we want to split our data into a train and test data set. So the first thing you want to do is you want to pass in all your data from your data frame into your X variable. And then your target values, these are keywords, by the way. So you can't really change this. This is what sklearn refers to as data. And this is target, meaning all of our values right over here within labels. That's going to be our target values. That'll be stored in Y. So that's what we do there. And then here, right over here, in this line of code, we are splitting our data into our testing data and our training data. So what I did was I set my test size to be only 10%. So 10% of the entire data set within the breast cancer data set is going to be used for the testing set. whereas 90% of the data we're going to be using is going to be for training the model in the training using the training set. So that's what the model selection, the train test split function does. And it'll store that data respectively within your training data and then your testing data. And you have to like follow this exact format, otherwise you will get an error that will be thrown at you. So yeah, so then if you want to see, okay, what is in my, what does my training data look like? What does my testing data look like? Well, I went ahead and I printed it right over here. So you could see that we have 512 total rows of data we're going to be using to train our model. And then our test set, we have 57 rows of data that we're going to be using to test our model. So, okay, right over here, within this list, this is all of our training data right here. So all of these values, 1.268E plus 0.1, that represents what is our mean, that's our mean radius for that first tumor. And then our mean texture is 2.384 plus 0.1. And if you guys want to know more about what these basic descriptions or these attributes are for a tumor, you can Google that. Since this is a machine learning tutorial, I figured it would be best if we stick to that. But you guys can look into that at your own time, by all means. Anyways, yeah. So each value is respected to the given attribute right over here. So we have mean perimeter, mean area, mean smoothness. All these values over here correspond to that. And our last value is this row right over here. Finally, you can see, okay, we have a bunch of zeros and ones. These zeros and ones represent the actual targets or the labels. So it represents 0 being, I think if I remember correctly, you have to look at the data set, but 0 being whether it's malignant and then 1 being whether it's benign. Cool. So that's basically what the expected labels are or expected outcomes are. So now that we've split our data into our testing and our training data, the next thing we want to do is we want to create our support vector machine model, right? So the nice thing is SVM from the library we imported in sklearn can be used to create an SVC. So this SVC function stands for support vector classification. And essentially, since we're building a classifier, that's the reason why we want to call this function. Here you can see that we set our kernel to be linear. So you probably remember that I mentioned something about kernels earlier. Kernels are basically functions used to compute the number of dimensions you'll need to help classify the data and also help determine where should your hyperplane be placed. So here we're using a linear kernel, meaning it's like just x plus y. You just want to make sure that if you're using the linear kernel, it'll be like what we saw earlier. So if I go out, just give me 1 second. So this is like what an example of a linear hyperplane is. That's what we're implementing in our code right over here. And then this is our constant. This is just our constant to set to. It's one of the parameters that you need to pass. Honestly, you could play around with this. I didn't cover it too much, but you can look more into it within sklearn. If you type in sklearn and then SVM, it'll tell you more about this parameter, but it's just a constant that you can set to 1 or 2 or 3 that supports this kernel. I know that probably is like not the best explanation of what it does, but that is essentially something you might want to look into when you're reading about the SVM algorithm. So finally comes the simpler part where we just apply our model onto our training and on our training data. We're basically training it here. And after we finish training it by fitting it on our X-train and Y-train data, we test our model by calling the predict function on our testing data or X-test. So that'll be stored within our Y prediction variable. Now from there, all we can do is we can compute our accuracy. So using that metrics library that we imported from sklearn, it's really convenient because we can just call the accuracy score function. And we can call that function on our Y test data and also pass in our Y prediction data. What this will do is it will like automatically compute what your accuracy is based on what your predicted values are and what your tested values are. And I just converted this to a percentage and I rounded it up by 2. So here you can see that our model is 98.25% accurate, which is pretty damn accurate if you ask me. Yeah, moving forward. So we're almost done. So like I said again, here I just printed out the features because now in this next code block, I am going to print out all the values that were tested on our model and what were our predicted values. So here's what it looks like. This is a little bit less aesthetically pleasing, but you can see that our classifier predicted malignant based on this data that's been given of the following attributes right over here. And you can see that our actual value was malignant. Moving forward, you can see here we predicted it to be benign based on our actual values computed over here. And our actual value was benign. Moving forward, we could see that it's doing a pretty good job at making the right predictions. You can see that it's making the right predictions approximately 98.25% of the time, which means it's not 100% accurate. There will be times where like it will make mispredictions, but with the accuracy being so high and being so good, it's not going to be that often where we're going to find too many issues. Does that make sense? So yeah, this basically will go through the entire length of our predicted values, and it'll print out what our predicted value was. It'll print out what the values are for the test set from the test set. So that from that 10% of data that we have, it'll print out all the values from there. And then finally, it'll print out what the actual value was. And we can see that our model works successfully. So yeah, that's pretty much it, guys. That's how you create a model. Like if I were to zoom out, creating your model is it's only a couple lines of code. It's nothing too much. This is just the output. Let me scroll up. It's just a couple lines of code, lines of code where you have, which I broke into different code blocks. And I'll be sharing this notebook on Slack. I know I didn't send the other one yet. I completely forgot, but I will post that soon enough. But yeah, that's pretty much it. That's how you create your own classifier using SVMs. Does anyone have any particular questions so far?
I had one question.
Yeah, go for it, Michael.
So I'm just curious how when you're using supervised learning, how would that apply to something like a neural network where you're taking consideration of like weights and biases in something like backward propagation? I'm just curious, would we manually adjust those, or?
That's a good question. So there, like I said, that's more of a mathematical question. When it comes to computing those types of gradients and the weights, I would say I wouldn't say it's more manual. No, it's supposed to be it's supposed to be adjusting based on the actual formulas. I don't know too much about, I'm going to be honest, I don't know too much about how SVM directly relates to neural nets. But based on the different types of gradient functions there are, I would assume, I would guess that it's more, it adjusts on its own, if I'm not mistaken, with respect to the types of functions.
Okay.
There's a Slack channel. Yeah, there's a Slack channel. Does one of the officers want to send them the Slack link? If not, Jamie, go ahead and send your email, your ASU email into the chat, and one of the officers will add you.
Can I ask a quick question?
Yeah, go for it, man.
So, okay, this data set has a size of 569 and the dimensionality is 30. If I remember right, the one we did with the KNN was the used cars from Craigslist.
Yeah.
And it was 15,000 was the data set size.
Exactly, yeah.
I don't remember the amount of features or the dimensionality with that. But so the KNN's better for bigger data sets with less features.
Exactly.
And the SVM is, better for the contrary. So I'm just wondering if there's like a kind of a ratio you're looking for in terms of samples to features where you sort of you switch, you go with one model versus the other one.
Right. No, that's a great question. Actually, I can answer that question. So typically when you're trying to figure out what machine learning model works the best, there's a series of questions you have to ask. Are you trying to build a classifier, a predictor? What exactly are you trying to develop? From there, what if you decide to go down the classification route, there's no, I personally, from the projects I've worked on, there's no definitive number of attributes you can use to, there's no definitive number of attributes for you to state that, okay, this will work the best, this model, the SVM model will work the best for this project, or the Canaan model will work the best for this project. It's really up to you to test. Like, actually, like, so I didn't do this time, but what you can do is you can use KNN on this exact same training on this data set and train it with this data set and apply it on the same test set, the same 10%. And you can see that the accuracy is actually a lot less because we have more attributes we're taking into consideration. So it's really how you kind of have to play around with it and see which model works best for you. But if you remember, I think if I remember correctly, this was around 2 weeks ago, the number of attributes we used were around 5 or 6 attributes for the KNN model. Whereas here we're using like a total, I can't remember the count, but I want to say around like 20 or 30 different attributes. That's why we automatically know that SVM will work. Is the most optimal model to create for this case. Does that make sense?
Yeah, that makes sense.
Mm-hmm.
And then I guess it's probably a similar thing where you test and play around with it, but on your GitHub code, you actually did a test size of 20%.
Yeah, right, yeah. So you can honestly choose whatever. Keep in mind though, when you're adjusting the size of the test set, you have to be a little bit careful because you're sacrificing that extra data that you could be using for training. So meaning sometimes when you're training your model, your accuracy, if you don't save that model and you keep retraining it, sometimes your accuracy could be a lot lower because it's less data that you're training it on. Does that make sense?
I see, right.
So that model, so the code that I have on my GitHub, that's actually that's a different version. Like I just played around with this and then uploaded it to my GitHub. But it's pretty much the same. It should work just as well.
Okay, great, thank you.
Yeah, no problem. Cool. Does anyone else have any other questions? That's pretty much it though. That's what I wanted to share with you guys. How to implement your own model. You guys have the links within the chat. I'll upload this PowerPoint presentation onto our Slack channel. So just in summary, we went over what is SVM, what are some of the applications of SVM, and a basic implementation of a classifier you can use to identify whether a tumor is malignant or benign. Apart from that, that's pretty much all for the rest of this meeting. If you guys have any questions, feel free to ask and I'll stick around for some time. But if you don't, you're free to go.